Hey everyone, in this video we're gonna go over U-substitution. So I'm just gonna do an intro to U-substitution. So we'll do some basic problems to get a hang of what U-substitution is all about and do some examples, get some practice in before we move on to the more complex U-substitution problems. But with this first example, we want to find the antiderivative. So this is an indefinite integral. It has no limits of integration, so we're just finding the antiderivative of the function. So one way that you can do this is just use the distributive property. So I can just distribute the 2x in and rewrite the problem. So then I can just use the general power rule to integrate. So this is going to be 2x to the third plus 10x dx. And so now we can integrate this. So using the general power rule, what do we get? So we add 1 to the exponent, so it's 2x to the fourth over 4 plus 10x squared over 2 plus a constant, and then simplify. So this will be x to the fourth over 2 plus 5x squared plus c. And so this will be our antiderivative. But the other thing that we could do is, or make a U-substitution. So make a substitution, so we're going to use the substitution rule. And so what I do then, making a U-substitution, we see I'm going to let something be a different function, so we're going to change the variable. So I'm going to let u equal x squared plus 5. And the reason is because I noticed that when I take the derivative of u, so the derivative of u with respect to x, so du dx will be 2x. The derivative of 5 is 0. Now solving for du, multiply both sides by dx, I get du is equal to 2x dx. Or you can just think of it as doing the differential right away. So du will be 2x dx. And so now I can rewrite my integral with this substitution. So my new integral then becomes what? It will be the integral of, notice that I have the 2x dx. So this 2x dx is now what we're calling du. And then on the inside, I have x squared plus 5, but x squared plus 5 is u. So this is just u du. And notice that now this is a much easier integral to do. So what is the antiderivative of that? It will be u squared over 2 plus c. But then go back and plug in what u was. U was x squared plus 5. So this is x squared plus 5 squared over 2 plus c. So are they the same? They should be. What do you think? They don't look like they're the same, but if we multiply this whole thing out, you will see that they are in fact the same, right? If you multiply this out, what do you get? It's going to be x to the fourth plus, let's see, 5x squared plus another one of those. So 10x squared plus 25, and the whole thing divided by 2 plus c. So split up the fraction, so that's x to the fourth over 2 plus 10x squared over 2, so that will be 5x squared plus 25 over 2 plus c. So let's see, are they the same? Yep, I have x to the fourth divided by 2, x to the fourth divided by 2, plus 5x squared, plus 5x squared, and then I have plus c. So here, we do have the plus c, but what is 25 over 2? That is also just a constant, right? So we can just consider this whole thing is a constant. So we can just say that is the constant, so plus c. So then they are the same. So you can see how rewriting it and doing the distributive property, I get the same answer as when I change the variable and make it into a simpler integral, and then I can find the answer. The key here is going back to x's at the end, and so we get this exact same answer. So let's try another example. Now with this next example, here, notice that I can't quite do the same thing that we were doing here. Here I have the 2x times x squared plus 5. I can just distribute it in, and then I can use the general power rule. But here, I can't distribute the 3x squared inside the radical. So how do I integrate this? So here I'm stuck. And so this is where the substitution really comes in handy. And so when you're making a substitution, what you're really doing is think of it as you're changing the variable, right? It's almost like you're changing a language. So have you ever tried to learn a new language, a different language, whether if English was not your first language, then you probably had to learn English, right? Or if English is your first language and you're trying to learn something else, like in high school, maybe you took German or Spanish or Italian or French or Japanese, any other language, right? Then when you're trying to learn, what happens? So what I want you to think about is essentially your whatever language you're fluent in, that's the one that you do most of your thinking. Now, when you're trying to learn a new language, someone asks you a question in the new language, what do you do in your own head? Right? You translate it to your own language, for whatever someone asks you, then you translate it to your fluent language, and then you answer the question in your own language, right? In your head, this is what you're doing. But then what do you have to do? You have to translate it back. So that's kind of what we're gonna do here. So this X, right? X-ish is the language that we don't know so well. And so we want to translate it. And that's where the substitution comes in. We want to translate to, I'm going to call it U-ish. So you have X-ish. This is our languages. And you want to translate to U-ish. And then what do you need when you translate? You need a dictionary, right? Oftentimes that's what we use in order to make those translations. So you look up the word in the dictionary. So here, we need to figure out what is going to be our substitution. I want to let you be something. What do I want you to be? And the trick is you want to pick the appropriate you. You want you to be something from the problem that when you take its derivative, the derivative is part of the original problem. So let me just repeat that again. You want to let you be something that when you take its derivative, the derivative appears back in the problem. So here, for example, I have two parts. I have 3x squared and I have 1 plus x cubed. So if I take the derivative of 3x squared, I'm going to get 6x. Is that part of the problem? No. So I'm going to consider 1 plus x cubed. If I let u be 1 plus x cubed, what's the derivative? I'm going to get 3x squared dx, doing the differential right away. And that is part of the problem. So then that is what I want my u to be, because 3x squared dx is our du. And so this acts as our dictionary to help us make the translation, right? So now we want to translate it. So this is what I call my new integral. That's an n, not a w. Looks like a w. So my new integral is going to be what? It's going to be the square root of u, 1 plus x cubed, and then 3x squared dx is what I call du. And so now notice that this is something that we know how to do, right? We don't know how to do that, so this is the new language we don't know what to do with. We look up a dictionary and we translate the words, we translate our question, and now it's like, oh, and look at that. Now I can answer that question, right? This is the antiderivative of u to the 1/2 du, which I can just use the general power rule. But I'm not done. So I translated the question, but now what? I need to be able to answer the question in the U language. We need to translate it back to X. So we're going to look up in our dictionary again to be able to go back. U is 1 plus x to the third. So that means that this is 2/3 times 1 plus x to the third to the 3/2 plus c. And so that will be our final answer for this particular question. Now, the thing that I want you to also notice is when I have 3x squared times the square root of 1 plus x cubed, just as we have done in the past, I have given you a little warning that you can't do the integral of 3x squared times the integral of that, right? So this is not equal to that. You can't integrate piece by piece. When you have the integral of f times g dx, that does not equal the integral of f times the integral of g. So be careful about that. So this is where our different methods of integration are going to come in. Now the nice thing about finding the antiderivative is that you can always check your answer. So we found that the integral of 3x squared times the square root of 1 plus x to the third dx, if we found it to be 2/3 1 plus x to the third to the 3/2 plus c. So how do you check your answer? So to check, take the derivative of what you got, right? Take the derivative of your antiderivative. So 1 plus x to the third to the 3/2 plus c. So when I take the derivative here, what do I get? So I have a composition of functions. I have to do the chain rule. So I'm going to have 2/3 times, bring that power down. So 3/2 times 1 plus x to the third, then by the chain rule times the derivative of the inside, which is 3x squared, and the derivative of a constant is 0. And so notice here that my 2/3 essentially cancel out, and what are we left with? We're left with, oh, I forgot to do when you bring the exponent down, you decrease it by 1, so that's 1/2. So you're left with 3x squared times the square root of 1 plus x cubed. And that is what we had in the integrand, right? This is the integrand. So those are the same, so that means that we did it correctly. So this is really one of the nice things about integrals too, is you can always check your answer by taking the derivative. And so what U-substitution is undoing is the chain rule. Notice that we have a chain rule here. So U-substitution is undoing the chain rule. Right, going backwards, the general power rule is really what we've seen so far. So now we see a method, which is U-substitution, that is going backwards on the chain rule. When you get to Calc 2, you'll be doing methods that go backwards on the product rule, on the quotient rule, and on so many other things. So let's try our next example. So you have the integral of tangent to the third x times secant square x dx. All right, and again, big warning. What's the thing we cannot do? Right, the integral of f times g is not the integral of the product. So you can't say, oh, I'm going to integrate that and integrate that separately. You can't do that. So do we have a chain rule going on here? Looks like a product, but notice that you have tangent to the third x. And one of the things that I mentioned earlier was that how do you pick your u? You want to pick u to be the thing that if you take the derivative shows up in the problem. So here, do you see something that if I take the derivative, it shows up in the problem again? And hopefully you do. Notice that I have a secant square x. Who has a derivative of secant square? Tangent. So we're going to let u equal tangent x. You don't have to let it be each piece, right? You can just let it be the thing. I recognize, oh, secant square is a derivative of tangent, so I'm going to let u be tangent. And now when I find the derivative, when I find du, the derivative of tangent is secant square x dx. And now I have my way to translate this integral. So what is the new integral in terms of u? So the integral is going to be tangent to the third x. So tangent is u, so this is going to be u to the third times, and my secant square x dx, that's over here, secant square x dx. So that whole thing is du. So it's just going to be u to the third times du. And notice that now this is a much simpler integral to do. This is u to the fourth over 4 plus c. Are we done? No. You have to go back to x's. Back to whatever the original variable is. Back to the original variable. Unless you have limits of integration, you can then plug in the limits. So back to the original variable, this will be u to the fourth, but what is u? U is tangent. So this will be tangent to the fourth x over 4 plus c. And now that will be the solution to that problem. Let's try another example. Let's try this example. So this one looks like a polynomial. Also, I have 5x cubed times x to the fourth minus 2 to the eighth. Now, unlike the earlier problem, right, where we were able to distribute, here again, I can't distribute because I have to the eighth power. So I would have to multiply x to the fourth minus 2 by itself 8 times first before I could even bring in this 5x to the third inside. So we definitely don't want to multiply this x to the fourth minus 2 8 times. So this is where U-substitution comes in. So how are we going to pick our u? And what I want you to ask yourself is, does the derivative of one part equal another part of the problem? Maybe except for a constant. And so check the parts, right? So the derivative of 5x to the third, this will be 15x squared. Is that part of the problem? No. So what about, we don't necessarily have to take the eighth. What about just the inside? Most often, the u is something that's trapped inside of something. So because U-substitution is undoing a chain rule, so going back to the first and second problem, notice that here we let u be the thing in the parentheses, x squared plus 5. That was our u. Notice that here we let u be the thing inside the square root, 1 plus x to the third. And here, where's the other one? We let u be tangent x. So technically, you could say that this, you can write it as tangent x to the third times secant square x. So oftentimes the u is what's inside a parenthesis of sorts. So with that said, what makes sense for u here? And notice that if I let u be x to the fourth minus 2, what's the derivative of x to the fourth? 4x cubed, right? So then this is going to be, I'm going to let u equals x to the fourth minus 2. And then my du then is, I'm going to do the differential version, is 4x cubed dx. The derivative of minus 2 is just 0. And so does this show up in the problem? Yes, except for maybe a constant. So that's what I mean by, does the derivative of one part equal another part of the problem? Maybe except for a constant. Yes, here I have a 5x to the third and this is a 4x to the third, but don't let that be a barrier, right? Because I can see there's an x cubed dx. The variable part is what I'm trying to really go after. So that is what I want to then substitute. So I can say, well, x cubed dx is equal to du over 4. So then I can, for x cubed dx, I can substitute du over 4 in my new integral. So what is the new integral then? In terms of u, this is going to be, I can leave the 5 there. So it'll be 5 times, and that's going to get substituted by du over 4. And we're going to put that at the end, right? Our d, our differential part, always goes at the very end. We're used to seeing the integral as f of x dx. So when I change it to something else, it will be g of u du. So your differential always goes at the end, whatever your variable might be, right? H of t dt. So you want to make sure that when you make that substitution, your differential is at the end. So I'm going to have x to the fourth minus 2. That's what we call u. So it'll be u to the eighth. And then my dx is x cubed dx is equal to du over 4. So that would be du over 4. And so I can then pull the constants together. So 5/4 u to the 8th du. And properties of integration tell us I can take that constant out, so I can do 5/4 times u to the 8th du. And now that looks like a general power rule problem rather than some extensive multiplication problem. So that is the nice thing about U-substitution. So this becomes 5/4 times, now do the antiderivative of this, will be u to the 9th over 9 plus c. Are we finished? No. Go back to the original variable, in this case, back to x's. So that means this will be 5/4 times u to the 9th over 9. And what was u? We go back to our dictionary, right, where we made our u substitution. U, we said it was x to the 4th minus 2. So u to the 9th will be x to the 4th minus 2 plus c. Don't forget the plus c. And then I guess we can combine our constants. So 5, what's 9 times 4? That's 36. And then x to the 4th minus 2 to the 9th plus c. My 9 looks a little funky. So hopefully you're starting to get the hang of U-substitution. So it's essentially a way to make the problem simpler. Let's try our next example. All right, so in this one does look a little bit more intimidating. You have e to the 1 over x squared and then the whole thing divided by x to the 3rd dx. But again, we want to focus on, okay, if I'm going to make a U-substitution, does the derivative of one part equal another part of the problem? I guess one of the things you should probably first be asking yourself is, can you do the problem just by the methods that you already know, like general power rule? Is it the antiderivative of something you already recognize? But this isn't the antiderivative of something we recognize. Like if I saw e to the 2x, for example, I'll say like, oh, I know that's e to the 2x over 2 plus c. That's what I mean by something recognized. The derivative of secant x, or the antiderivative of secant x tangent x dx would be like, oh, that is the antiderivative, that is just secant x plus c. So that's what I mean by something you recognize. So here, that's not something we can just do by looking at it. If you can do this just by looking at it, then you need to show me how you do that. So we have to then, okay, what do I do? This is the antiderivative. I know that this is a quotient, but remember we're doing antiderivative, so don't bring in derivatives in here. Don't start doing quotient rule. So we're going to do U-substitution. That's the derivative of one part equal another part of the problem. So my u, let's see, if I do u equals x cubed, that's not going to help me. So let u be 1 over x squared, so the exponent of e. And then when I take the derivative with respect to x, right, this is x to the minus 2. So notice that now when I take the derivative, I'm going to get minus 2x to the minus 3 dx, which, ta-da, it is, I get the 1 over x cubed dx. So there is my dx over x cubed, and so there is my dx over x cubed. So that means that dx over x cubed is equal to du over negative 2. So that's what I'm going to substitute for that little square thingy. Looks like a little Christmas stocking. So for boot. So the new integral, what is the new integral become? Once you start substituting, then it's going to be the integral of e to the 1 over x squared, so e to the u, right? We let u be 1 over x squared, times dx over x to the 3rd. Dx over x to the 3rd, we said, is du over negative 2. Now, with properties of integrals, we can bring that constant to the outside, right? This is really a negative 1/2, so bring the negative 1/2 out, and you have e to the u du. Now this is something I recognize. The antiderivative of e to the u is just e to the u. So I'm going to have e to the u plus c And are we finished? No. Go back to the original variable. So this is -1/2 e to the, what was u? Go back to what your substitution was. If you don't remember, u was 1/x². So this is e to the 1/x² plus c. Pretty cool. U-substitution is going to become your friend. Once you start learning the other methods that you will learn in Calc 2, you're going to want to wish that everything was a U-substitution problem, even though the other methods are super fun. It's one of the reasons I love Calc 2. Calc 2 is sort of like a big puzzle that you have to put together. You have to look at integrals and see what method do you use. You have like 6 or 7 or 8 different methods to use to solve an integral, and it's just kind of fun to try to figure out which method applies. And so for some of us that is really fun. For some people that makes Calc 2 very hard. So you'll have to let me know after next semester which team were you on. Did you enjoy the puzzle of the antiderivatives of the integrals, or did it become too complicated? All right, so this is a definite integral now. So we have limits of integration, so we're looking for the area between the curve and the x-axis. Net area, right? I don't have an absolute value here, so I'm not looking for the distance. I'm looking for the net change. So let's see. Can we do it just by looking at it, right? Is this something that we know how to anti-differentiate? But it isn't. So then the next question is, find u. Does the derivative of one part equal another part of the problem? And this is one of those puzzle ones that I was talking about, because it doesn't look like it, right? You have x to the 4th plus 1. The derivative of x to the 4th is 4x to the 3rd. I don't have an x to the 3rd. So what in the world do we do? I need to find a u because I don't have any other way to solve this. So check this out. And this is, again, one of the reasons I absolutely love Calc 2. You're going to have 3x over, let's rewrite that x to the 4th. X to the 4th is really x squared squared. Why did I do that? Do you see it? Is it clicking? Now I can let u be x squared, because then du is what? 2x dx, and I can find x dx is in the problem. There's the x dx, right? So then that means I can take this problem, take the 3 out, and say x over x squared squared plus 1 dx. And with this substitution, the new integral will be 3, the integral of x dx, which is, solve for your x dx here. So what is x dx going to be? Du over 2. Divide both sides by 2 to get just dx dx, the stuff in the box. So then I'm going to have, this will be x dx gets substituted by du over 2. So I'm going to put the 1/2, I don't want to confuse you too much. I'm going to put the 1/2 outside and the du on the top. And then the bottom is x squared, but that's u, so it's u squared plus 1. And I already have my du there. How is that? So what did we do? So we noticed the powers weren't working. So normally when you have polynomials, this is another kind of cool little trick. You want your u and your du, if you have polynomials, to only differ by 1 degree, right? Because that means that if you take the derivative, you decrease it by 1. So you only want your degrees when you see polynomials to differ by 1. So I have an x. That means that ideally I would want to have an x squared there, which is why then I chose to write that as x squared squared. That's still x to the 4th, but this allows me to change that to a u. And now I can translate it. And so now that I have this translated, we can solve it. Before I move on to that, I want to make sure that we are okay with how we got this du and the 1/2 there, right? When you try to pair, so you look at your du and what in your du matches up with the original problem. And so that's why I boxed up the green stuff. So now I'm going to highlight it, right? I'm looking at my du, that matches up. the constants don't have to match up, right? Because constants, we can just manipulate them. The 3 gets pulled out. This, when I solve for the stuff that's highlighted, then that x dx is what I'm going to substitute in the original problem. That becomes du over 2. So then what I did with this du over 2 is I wrote it as 1/2 times du really, so that my goal is to be able to write this as g of u times du, right? Your differential is always at the end of the problem. So your du, dt, dx is never going to be an exponent. It's never going to be in the denominator. It's never going to be inside a parentheses. This is the differential, so it's always on the outside, like times du, dt, dx, whatever it is. So now we're ready to move on, hopefully. So this is 3/2 the integral of, and you can, if you want, you can just rewrite it as 1 over u squared plus 1 du. And do we recognize that? Hopefully we do. This is inverse tangent of u. And I will do plus c, but I have not forgotten that this is a definite integral. But notice that I didn't write my limits of integration anymore. Can you think of why not? So why didn't I take my limits of integration with me? And the reason is because these are what kind of values? The 0 and 1 are x values. So that's x equals 0, x equals 1. Once I translate it, this is no longer 0 and 1, right? This then should be u values. So I'm not going to write those down. Instead, I'm going to go back to x's, back to the original variable. And so this will be 3/2 inverse tangent of u. Remember, u was x squared. And now I'm going to say from x equals 0 to x equals 1, right? So I don't want to make the mistake of saying 0 to 1 here, because those may not be my same u limits. I think in here they are, just because of the uniqueness of the 0 and 1. When you square them, u is x squared. So when you square 0, you get 0. When you square 1, you get 1. But that's not always the case. So just be careful about that. So I oftentimes leave them and then put them back in at the end when I change back to my original variable. And so now evaluate it. So this will be using the fundamental theorem of calculus. Plug in the top limit first. So that will be 1 squared, which is 1, minus 3/2 inverse tangent of the bottom limit. And inverse tangent of 1 is pi over 4. And inverse tangent of 0 is 0. So our final answer then is 3 pi over 8. Cool. All right. So I'll end there. So I'll let you try the homework. Try to practice figuring out what your u is going to be, and try to ask yourself that question, right? You pick u based on, if you ask yourself, does the derivative of one part equal another part of the problem? If the answer is yes, then the thing that you're taking the derivative of, that's your u. So here, the derivative of x squared is 2x. So I have my x dx. In this one, the derivative of 1 over x squared gives me the 1 over x cubed. So that's how I pick my u. Here, the derivative of x to the 4th is 4x cubed dx. So I have my x cubed dx, so I let u be that, and so on. So ask yourself, does the derivative of one part equal another part of the problem? As soon as you answer yes, that means you're doing a U-substitution, and let u be the thing that you take the derivative of. Email me if you have any questions.